Good afternoon, everyone. Today we are talking about experiment number 2, identification of a compound, chemical properties. This is the experiment I'm hoping you'll be able to do on your first actual day in person lab. We're going to try to do both basic lab operations and this experiment in one day, so that you can later use your time off lab and away from the classroom to finish up your reports. This experiment actually utilizes your knowledge of chemical reactions and your ability to predict and explain when reaction is about to happen and which criteria we can use to decide whether reaction will occur or not. So in this experiment, you're going to first deal with 5 known liquids, and you're going to treat each one of the known liquids with each one of the 3 test reagents. And you're going to make observations and see which combinations of known and the test reagent did produce a reaction. And then based on those observations, you should be able to identify at least one unknown. We will see how it goes. There may be 1 or possibly 2 unknowns you'll have to identify. Those unknowns will be from the same list as knowns, but this time you won't know what they are. So you're going to test them with each one of the 3 test reagents once again and match your observation on an unknown with one of the knowns. And you will also have to write chemical equations, at least molecular chemical equations, for those combinations that did produce a chemical reaction. I would like to point out that before you start working on this experiment, it is highly recommended, as part of your homework assignment, to carefully read the handout about writing chemical equations for ionic reactions that is available on Canvas. I did put this handout together myself, hoping to give you a quick review of how formulas for ionic compounds are put together based on the charges of ions involved, and which criteria can be used to predict which reaction between 2 ionic substances in aqueous solutions will occur. So in this experiment, we have 5 known solutions. So all of them are aqueous solutions, obviously liquids. One of them is pure water. Notice the subscript L. L stands for liquid. Do not confuse it with subscripts for others here. AQ stands for aqueous. There is a difference. Liquid means pure liquid substance, like in this case water. AQ means aqueous, which means the substance either solid or liquid or gas even dissolved in specifically water. So you have 1 pure water, as you know, and 5 aqueous solutions of ionic substances. The 4 ionic substances used as knowns here include sodium chloride NaCl, sodium carbonate Na2CO3, magnesium sulfate MgSO4, and ammonium chloride NH4Cl. Just a quick reminder, the subscripts that we use here are based on the charges of ions. Now, what you must know for this lab is names and charges of several basic polyatomic ions. I will briefly refer you to one of the appendices at the end of the lab manual that can be used as a reference should you need a quick reminder of the name or the charge of a specific ion. So this ion here is called carbonate. It's a polyatomic ion, formula CO3, and the charge of this polyatomic ion is -2. Sodium has a charge of +1, so you need 2 sodiums per 1 carbonate to make sure the overall charge is 0. Whenever you're writing a formula for a ionic compound, you must make sure you take into account the charges and use subscripts where appropriate. I will point some other examples as we go through some of the equations that we will be discussing. Magnesium sulfate, no subscripts here because magnesium is +2. This here is sulfate ion, SO4, polyatomic ion, and the charge of sulfate is -2. So +2, -2, 1 of each produce overall charge of 0. Finally, this one here is called ammonium chloride. NH4 plus is the only probably polyatomic cation or positively charged ion you will be encountering for a while. So you need to know that this here is called ammonium cation and a charge of +1. Chloride ion has a charge of -1, so once again, +1, -1 produce a particle, 1 ion each with an overall charge of 0. The test reagents you're going to be employing in this experiment are listed on page 68 of your lab manual, so hopefully you have your lab manual handy as you're watching this video. And the test reagents are listed right under the knowns, and they include silver nitrate, AgNO3, sodium hydroxide, NaOH, and hydrochloric acid, HCl. All of the test reagents are also going to be as aqueous solutions. I would like to point out that for this experiment we are only doing part A, and so we're going to look at reactions between knowns and test reagents, and then unknowns from the same list. So unknowns will be from the same list as knowns. No new chemicals will be introduced where unknowns are tested. So here I have a summary of all the subscripts we use to designate the state in which a reactant or product is present. AQ aqueous, L liquid, G for gas, S stands for solid or precipitate. This is possible that this might be confusing because you may think S soluble. In fact, it's exactly opposite. It's an insoluble. Something that's insoluble in water or has very low solubility will produce a precipitate or a solid product. So S stands for solid. Keep that in mind. So the question that I sort of alluded to earlier is, how do we know when a reaction between two ionic substances in aqueous solution, in other words, when we combine two aqueous solutions, how will we know that reaction will occur? And there are three very clear criteria that can be used to predict this particular type of reaction. Now, this is much more narrow of a criteria set than in general. If you ask, how do you know there's a chemical change, you might say heat is produced, you might say color would change, things like that. This is slightly different. This refers to strictly ionic substances reaction in aqueous solution. And so this is a type of reaction called double replacement. And the three criteria that we're going to discuss is actually all discussed in detail with relevant examples in that handout that you're expected to carefully study before coming to lab on the day when we're doing this experiment. First of those criteria is formation of water. So an example would be so-called neutralization reaction. It's a reaction between an acid and a base that produces salt and water. I used sodium hydroxide as an example of a strong base, and hydrochloric acid as an example of a strong acid. These red lines up there and down here show how ions basically switch partners. So sodium is going to be now paired up with chloride for the product, and hydrogen is going to be paired with hydroxide. And so the products will be sodium chloride, aqueous, and water. And in this reaction, it will be hard to actually observe it. We typically need to have an acid-base indicator telling us that this reaction has occurred. This type of reaction between an acid and a base producing water will not be part of this experiment. We will, however, look at acid-base reactions later when we perform an experiment dealing with titration. We will look at these reactions in detail then. Second important criterion that can be used to predict that reaction will occur to completion is formation of a precipitate or water-insoluble product. And so this type of reactions are going to be the focus of this experiment today. And before we look at an example of such reaction, I'd like to call your attention to couple of appendices at the end of your lab manual. First one of them is Appendix B, pages 200 to 201, gives some familiar names of chemicals and their respective formulas. There's also Study A2, pages 202 through 205, some useful examples of charges of ions and examples of how to write formulas of equations. And finally, the most important appendix for this experiment is Appendix E. It starts on page 208, but most importantly, the page you want to be consulting for this experiment is page 209. It's table E1, summary of solubility of salts. So here you have, in the first column, anions or negatively charged ions listed in alphabetical order. You have a name, chemical formula, and the charge of each ion. And then the second column shows which salts are soluble with the cations from this column, and insoluble salts with certain cations for this anion are shown in the last and third column. I would point out here that insoluble here is shown in quotes. It's not a coincidence and it's not a minor detail. This is because in nature there are no truly insoluble materials in water. Everything to a degree is soluble in water, but some things have extremely low solubility, and so they appear as though they are insoluble, and those would be the ones that produce a precipitate. We will discuss use of this table in class. Hopefully your TAs will be able to explain a little more, but I would strongly encourage you to take a look at this and figure out how this table should be used for lab. So back to an example. The example I picked for discussion is a reaction between one of your knowns and possibly unknowns called magnesium sulfate and one of your test reagents, which is sodium hydroxide. So what would happen if we mixed these two clear colorless aqueous solutions together? Well, first we have to figure out products. And one of the reasons I picked this particular one is because, as you will notice, the subscripts will change. So here I have to pair up magnesium with hydroxide. This is what this red line represents. Remember, double replacement, so they trade partners. And sodium would be paired up with sulfate. Things to remember here. First of all, when writing a chemical formula for any ionic compound, cation must go first. Second of all, overall charge of any product you write, in order to make sure your chemical formula is correct, the overall charge must be 0. So in this case, let's start with reactants. Magnesium has a charge of positive 2. How would you know that? Well, magnesium is one of the main group metals in the periodic table, and it's in group 2, so usually for main group metals, the number of the group matches the charge of the ion the metal is most likely to produce. So magnesium is positive 2. As I already mentioned, this here is sulfate, and sulfate has a charge of negative 2. And then sodium is positive 1 because sodium is in group 1 of the periodic table. Hydroxide, another one of very common polyatomic ions. You need to know its name and its charge. You must memorize it. So hydroxide is negative 1. So now I'm combining magnesium with hydroxide. Notice how the chemical formula of the product is written. It's not just MgOH, it's MgOH2. Why did I put 2 here? Well, magnesium is still positive 2. Remember, charges do not change in this type of reaction, unlike in, say, redox reactions, which we will discuss later. So here magnesium stays as positive 2. Hydroxide stays as negative 1. In order to make sure the overall charge is 0, we need to have 2 hydroxides per 1 magnesium. Notice how I put hydroxide in parentheses. This is typically done when you have more than one polyatomic ion in the compound. These parentheses are very important because they show there's 2 hydroxides per 1 magnesium. And then the second product would be sodium sulfate. So we're pairing up sodium with sulfate. Cation always goes first. You'll notice I have 2 next to sodium. Why did I have to put 2 next to sodium? Well, sodium is positive 1, as we mentioned before, and sulfate is negative 2. In order to make sure overall charge of this formula is 0, we must have 2 sodiums per 1 sulfate. So these subscripts, this one here and this one here, were placed there in order to correctly write the formulas of the products. These subscripts do not get carried over. For example, here sodium did not have a subscript, and here it does. This is because it's paired up with an ion of a different charge than before. And so it's important for you to keep that in mind. Now, let's look at subscripts. This is aqueous, this is aqueous, and then all of a sudden I have S here for solid, and this is aqueous. And the fair question to ask here would be, how did you know? And the answer is, you would look it up in a table that I just showed you in Appendix C on page 209. What you would do is you would find hydroxide in the first column, and then you would look in the first column, and it will probably tell you it's soluble with some ions, but then it would list magnesium as one of the insoluble ones. And so this is how you know that if you combine magnesium with hydroxide, you would get magnesium hydroxide, which would be water insoluble. Now I'd like to show you how to write what's called ionic equations. These will not be required, but it is highly recommended, at least I recommend it, so that you try to write them. For ionic equations, you split up all reactants and products except for 3 things that we already mentioned today. You can probably guess what those are. One is water, second one is precipitate, and I don't think I mentioned the third one. Third criterion that predicts that reaction will occur in aqueous solution between ionic substances is formation of gas. So water, precipitates, and gases are not split into ions. Everything else that has aqueous subscript next to it can be split into ions. For example, when you dissolve magnesium sulfate solid in water, it splits up or dissociates into magnesium plus 2 ion and sulfate ion. Similarly, if you dissolve sodium hydroxide in water, it will exist as sodium and hydroxide. One other note, you'll notice once I have to place these subscripts here for my products in order to have correct chemical formulas, you need the rows for balancing the equation. Thing to remember here, you cannot balance equations by putting these subscripts into the formulas at will. These subscripts depend on the charges and cannot be altered. For example, you could not just put Na2OH right here. Instead, what you do is you use what's called coefficients. Coefficients show how many units of each substance are participating in the reaction. Because I had 2 hydroxides and 2 sodiums here, I have to put 2 in front of an AOH in order to make sure my equation is balanced. And I have 2 sodiums on each side of the equation and 2 hydroxides. So how do we then write a full ionic equation? This here, of course, the top one, would be called the molecular equation. To write a full ionic equation, I'm splitting everything up except for magnesium hydroxide. Why am I not splitting magnesium hydroxide? Well, because it is a solid, it's a precipitate. And remember, we do not split precipitate. So these are my reactants: magnesium plus 2 plus SO4 2 minus, 2 sodiums, 2 hydroxides. This is my product side: magnesium hydroxide, solid, plus 2 sodiums and plus 2 sulfates. Notice how the subscript up here for sodium sulfate becomes a coefficient, showing that when sodium sulfate dissolves in water, there are 2 sodium ions being produced in solution. So now if we compare the reactant portion of the equation with the product side of the equation, we may notice that there are some ions that have not changed a bit. They're still in the same exact shape and form. And I hope you can see that such ions in this particular example include sodium and sulfate. There's two sodiums here, sulfate, sulfate. These ions are referred to as spectator ions. And so such ions are typically excluded from the initial full ionic equation, leading to what's called net ionic equation. So net ionic equation would, in this case, look like this. Magnesium 2 plus, adding 2 hydroxide ions produces 1 unit of magnesium hydroxide precipitate or solid. Notice how much shorter the net ionic equation is compared to molecular equation. So there's definite advantage for writing net ionic equations. And if you're not familiar with them, or you don't remember very well how to write them from high school, I would definitely recommend you try and work on some of these. This will make it easier when you have to write them for lecture. It's one of those things you cannot pass general chemistry without being able to write these equations. Next, we're going to consider two important reactions, both important reactions for this particular experiment, which involve formation of gases. And with gases, the difficult part always is to make sure you can detect formation of gas. With precipitate, it's obvious because your mixture becomes cloudy. But with gases, it's a little trickier. So how do we figure out when gas is produced? I'm going to show you both reactions from this experiment. Those are the only two where gases are produced, and I'm going to explain for each one how you detect gas being produced. First reaction here involves another one of your knowns called sodium carbonate and another test reagent called hydrochloric acid. Once again, double replacement reaction. So sodium is going to be paired up with chloride and hydrogen with carbonate. Notice, by the way, that this subscript here is not going to be carried over into the product side because of the charges. So sodium is +1, and the reason why it has 2 right here is because carbonate is -2. But on the product side, sodium is now going to be paired up with chloride. Sodium is +1, chloride is -1, so we only need 1 of each. And then the second product of the reaction is a very interesting substance. It's hydrogen paired up with carbonate, which produces a substance called carbonic acid, H2CO3. Now, carbonic acid is a substance that is undoubtedly familiar to you if you ever had any type of sparkling water or pop. Carbonic acid is something that you drink. Carbonic acid is a very weak acid. It's the only acid I know of that's safe to drink in any quantities. It's not going to harm you unlike any other acid. And carbonic acid, being a very weak acid, quickly breaks down. It's unstable, and so it quickly breaks down into carbon dioxide gas and water. So the gas that you're detecting here when combining sodium carbonate and HCl would be carbon dioxide gas. I would also point out that carbonic acid is actually a component of our blood. It is needed in the blood in order to prevent pH from changing. We will talk about that in detail when you take general chemistry too. So for now, let's take a look at net ionic equation for this reaction, and then we'll talk about how we know that carbon dioxide is being produced. So for full ionic equation, again, I'm splitting everything up except for carbonic acid, which forms CO2 and water. CO2 is a gas, water is a liquid, so neither one of these should be split into ions. So for sodium carbonate, I have 2 sodiums and 1 carbonate. I had to balance the equation in order to make sure I have equal number of atoms of each kind. So I had to put 2 in front of an HCl and 2 in front of HCl here. And so for HCl I have 2H plus and 2Cl minus. And then here I made 2 sodium chloride units, so I split them up into 2Na and 2Cl. These red dashed lines represent spectator ions. As you can see, there's 2 sodiums and 2 chlorides on each side of the equation. No change, so we can exclude them or get rid of them. And as a result, we're going to get a net ionic equation of the reaction between a carbonate and hydrogen ion, which is produced by acids, and you get carbon dioxide gas and H2O. So question is, how will we know that CO2 is indeed produced? And one thing I point out here, for those who are familiar with baking, you may know that in order to, if you're making a cake and you want it fluffy, to help the cake rise, you can either use yeast, which is a biological entity that produces CO2, or some recipes do not call for yeast. Instead, they call for baking soda and usually either vinegar or lemon juice. And this would be a very similar reaction that would then cause production of CO2. Sodium bicarbonate, NaHCO3, is what we know in everyday life as baking soda. It's a close relative of sodium carbonate we're using here. And of course, vinegar contains acetic acid and lemon juice contains citric acid. Both would then generate hydrogen ion. So net ionic equation for such reaction would be very similar to what we have here. So how do we know that CO2 is produced when we're making a cake and we're combining either baking soda or baking powder with, say, vinegar? Well, it produces a bunch of bubbles. So here CO2, having fairly low solubility in water, will be detected as bubbles. I would like to point out that in this lab, the concentrations of reagents is higher than what's recommended in your lab manual, and this is by design. That's something I asked our stockroom to do in order to make sure it makes it easier for you to detect the bubbles. But remember, it won't be nearly as spectacular, if you will, as if you open a warm can of pop. It won't foam like this, and bubbles should be looked for immediately after combining the reagents because they'll escape quickly. So make sure you look closely when trying to detect carbon dioxide. Finally, the third equation we're going to consider is the second example of gas formation in this experiment, and this time we're talking about ammonia gas. So the reaction here involves a third one of the knowns on your list, ammonium chloride, and we're considering what happens when we add sodium hydroxide, which is another test reagent, to ammonium chloride. Once again, double replacement reaction, so sodium is going to be paired up with chloride and ammonium ion with hydroxide. The products are ammonium hydroxide and sodium chloride. Here, no balancing is required because all ions have charge of either +1 or -1. However, one thing to keep in mind is an interesting feature of ammonium hydroxide. Ammonium hydroxide is what forms when ammonia and water combine, but it's unstable and quickly breaks back down into ammonia gas and water. In fact, we often in the lab refer to ammonium hydroxide as just ammonia solution. So if you hear your TA say you need to add more ammonia, it typically means more ammonium hydroxide. So ammonia dissolves in water, produces ammonium hydroxide, which then quickly breaks down into NH3 and water. So the gas that we're looking for here is not ammonium hydroxide per se, because ammonium hydroxide is aqueous. Instead, it's ammonia gas, NH3. And the tricky part here is to be able to test for ammonia. Unlike CO2, ammonia is extremely well soluble in water, and so it will not produce bubbles. So looking for bubbles here is sort of useless. So the question then becomes, how do we know if ammonia has been produced? Well, if you look in your lab manual, the lab manual talks about smelling the container in which you think ammonia may have been formed, because ammonia has this characteristic smell. However, the amounts that we're dealing with here, this is sort of a microscale experiment. We're only using drops of solutions here. We're not using large amounts and concentrations, while higher than recommended in the manual is still fairly low. And so smelling it may not be reliable. So I'm going to explain how you're going to detect ammonia in this experiment, which is different from what's in the book. First, I want to show you this. This is the well plate you're going to be using to conduct all these reactions. You're going to place your knowns across, and then you test reagents down, each time noting which chemicals you combined in each well and what kind of visual result, such as, say, precipitation or bubbles or formation of gas, you may be able to detect. And so let's say you need to test for ammonia. One thing we can use, which is much more reliable than smelling, would be the fact that ammonia is basic. And because ammonia is basic, we're able to detect ammonia vapor, ammonia in gaseous form, using what's called red litmus paper. So cylinders like this will be given to you. There will be at least one on each bench. This is called red litmus. Litmus is one of organic compounds that change color based on how basic or how acidic a solution is. They're called acid-base indicators. And so by using this, you can actually tell if an acidic or basic substance is present. Particularly red ammonia is used to, red litmus is used to detect bases. So red litmus, if it turns blue, indicates presence of base. It's easy to remember, blue base. So what you're going to do is you're carefully going to open the container, you're going to tap on it, and you're going to get a strip like this out. You're going to hold it on one end like this, like I'm doing now, making sure the other end that you're going to use for testing is not contaminated with any chemicals. You may put it down if you need to, but only on a clean surface. Don't put it on a dirty bench. Put it on a watch glass or some other clean surface if you have to. So what you're going to do is you're going to take a strip like this, and you're going to dribble a little bit of deionized water on it. This paper only works when it's wet. And then you're going to combine your two reactants. So first make sure you get litmus ready. Then combine the reactants, and then you're going to hold it like this, flush with the well. Do not dip it in liquid. Remember, you're trying to detect a gas, so dipping it in liquid is incorrect. It will not provide you with accurate information. Instead, you want to hold it like this, flush with the well, hoping that the vapors of ammonia produced in the reaction will penetrate the paper and turn it blue. Now, one possible difficulty you might experience is that, as you can see, wells are really close by. And so sometimes you're testing, and ammonia may have formed in the neighboring well, and you're testing the next one over, and you're still getting false positive because ammonia vapor sort of drift over here. So if you think that might be a possibility for any of your unknowns, for example, I suggest you run the same test in the medium-sized test tube. Just make sure the test tube is clean. Add your chemicals, and then place the strip in the test tube without touching the liquid. Test tube is more isolated than these wells, and so it may be more suitable if you need to confirm positive test for ammonia. Use strips should not be put in the sink. They should not be left on the bench. Please make sure to use a trash can next to your seat in order to place the used strip in there. The containers with indicator paper must always be kept tightly closed to avoid vapors from around the lab from contaminating the unused strips. So let's briefly talk about your report sheet. We're looking at page 73. Remember, you will not have to do part B, so we're only doing part A. and this is the only portion of this page you're responsible for filling out, and you will be given time outside of class to complete your work. I would just point out that in the top portion of your report here, you will be recording your observations. So if no reaction occurred, you put NR. If a precipitate has formed, if you see formation of solid particles, you put P for precipitate, or you may put S for solid, or you may put C for cloud. It's the same thing indicating precipitate. And then for gas, if you see bubbles, you would put bubbles, and if you use litmus paper as I just described, you would put red litmus turns blue. Remember, not all of these will produce a reaction, so there will be some that will say NR. And then the second portion here says write formulas for the precipitates that formed in part A. Here, after word precipitates, I would like you to add and gases. And then before you fill this portion out, you will have to take a separate piece of paper and write chemical equations for all reactions that you observed as occurring. So as a minimum, you write molecular equations, make sure they're balanced. And again, it's highly advisable that you try to write ionic equations as well. And then down here, you will be identifying your unknown. And we will let you know whether you will be doing only one unknown for part A4 or possibly two. This is all.